Okay, so I will be talking about the low and high mass Higgs boson searches in CMS, and mainly the neutral Higgs sector, because the charge Higgs I already discussed in the previous talk. So I have prepared my slides accordingly. So as these things are many times discussed during this meetings, but I would still like to go through why we are hunting Higgs-like particles. So the observation of the new Higgs-like particle in 2012 around 125 GeV is pretty close to the standard model prediction, and until now we haven't seen any deviation of its properties from the standard model predictions. But still, I mean, even though the standard model hasn't yet been falsified by any experimental evidence in LHC, but still standard model leaves ajar the door for further model building, which actually explains some of the experimental observations outside LHC, and mainly the dark matter, the observation from the galactic rotation curves. We know that there should be some kind of matter which is not visible and weakly interact with other particles, and also now it is established that neutrinos has mass, which is also not incorporated in standard model. And recently we have seen that the magnetic moment of muon, the prediction from standard model and the observation are not matching within some standard deviation. So that means there should be some theory which will explain the current observations, which the standard model can predict, and should also explain the observations that standard model cannot predict, and that should be called as the complete theory. And it is expected that those theories that can explain these phenomena, they also brings some ideas of new particles, like the Higgs particle that we had few years ago, when it was not explained, not experimentally found. So similarly, we have many particles that other theories predict, and so we actually are trying to investigate using the experimental data if we can see such particles that those theories or models are predicting, to understand this unexplained phenomena. But the hypothetical existence of new particle raises questions such as then this standard model Higgs boson that we have observed, is it really standard model, or it is a part of a bigger theory? And the other questions, like, is it the lightest Higgs boson, or some it is not the lightest, but maybe there is another Higgs boson which is lighter than the one that we have found. So basically there are many theories that predicts multiple Higgs, and here I just have shown a few minimal extension of the standard model namely the MSSM. And we see that if we add another complex scalar doublet to the standard model, which is the 2 Higgs doublet model, after the electroweak symmetry breaking, we get 5 Higgses, and out of them 3 are neutral and 2 are charged. And the main parameters of this theory, after many constraints that we have in MSSM, reduces to 2, which are tan, beta, and MA. And also people have, as more and more data has been taken in LHC, and we are ruling out several phase spaces of the MSSM. New theories and models are coming up, which actually keeps almost the same features as MSSM, but can have particles which are basically have properties that can be searched in LHC experiments. And for that, we have another extension to the standard model, which is adding another singlet to the standard model, and by that it actually increases the number of Higgses to 7. And not only these, I mean, there are multiple other models that predicts Higgs, like the dark sector, and also Higgs triplet models. But right now I will be only concentrating on the above models that I already said. And how at LHC we are searching for these phenomena are 2 ways. I mean, one is the indirect way, and the other is the direct way. So what we can do is using the existing 125 GeV Higgs, we can see if the width of the Higgs is what is predicted by the standard model, or it is slightly deviated. And we can also try to find out if there are some invisible decays or left-hand flavor violating decays or long-lived particles that into which the observed Higgs can decay into. And that is the indirect way of searching the beyond standard model Higgses. And the other way are, obviously, we can directly search for the resonances, as we can see that if for the low mass resonances like Higgs decaying to 2 pseudoscalar small a's, which are lighter, and they can decay into BB bar or muons or photons, etc. And also we can search for Higgs, lighter mass Higgs, lighter than 125 GeV, I mean, lighter mass Higgs directly to photons with a top or bosonic loops and W loops. And also for the high mass, as we already have seen for the charged Higgs, it was discussed in the previous talk, but also for the neutral Higgs, they can decay into WW or some other pair of particles, triphoton also, and one can search for new particles, either resonance or excess, in the various observables of the particle in the experiment. Now, there have been multiple analyses which are performed and being performed with the LHC data in CMS. Some of them include full run-to data and I will try to concentrate on those mainly which actually have already analyzed full run-to data. But there were also some old results that already has exclude some phase space of these theories. And here I have quoted a few which actually are searching for low mass pseudoscalar or Higgs, as you can see. And the high mass, as I already mentioned, I will be mainly talking about the neutral Higgses. So they can decay into either third generation quarks like top or they can also decay into the diboson like GH or WW or WA. So as I already mentioned, that I will not go through all the searches, firstly because they haven't yet analyzed the full run-to dataset, and also because of the time constraint. I will only concentrate on these three analyses that has been, out of these three, the two has been recently published their results, and one is my analysis, so I will talk about that, even though that is old, but we are still analyzing the run-to data, and we will be publishing results of that soon. So starting with the first analysis, which is Higgs decaying to two pseudoscalar, and they then decay to diphoton. So in this analysis, as I said, the Higgs, it is an exotic decay of the Higgs into a BSM pseudoscalar particle, which further decays into photons. And this basically is a model independent analysis where the both photon pairs have wide opening angle. So we actually have a separate analysis for boosted topology and non-boosted topologies. And the one that is already published is non-boosted search, but the boosted topology is still being analyzed for that phase space. That is being analyzed. So here I will talk about the non-boosted phase topologies, and that is why I mean the photon pairs are well resolved, and they are reconstructed separately. There is no overlap between the clusters of the photons in the electromagnetic calorimeter, and that is why the window in which we can search for this kind of a signal is not very wide. It is from 15 to 60. So if you go very low MA, then it starts to starts to become the photon starts to become resolved. Unresolved, and that is not what this analysis is aiming for. So yeah, I mean, so that actually decides the range of the pseudoscalar mass in which this analysis is this analysis is interesting because the coupling of this, though the coupling of this pseudoscalar to the fermions can lower the branching ratio of this pseudoscalar to the diphoton, but in this signature final state, the amount of background is pretty small and can be well modeled, which is not always true for other kinds of decays like BB bar and others. And also in some models, the pseudoscalar may only decay into photons. Okay, so then coming to the event selection. So I will just go through this for only one analysis, but not for the others. just to say that we in CMS, we have multiple layers of selections that we apply to reduce the background as much as possible. And at the first place, we have the online selections, which are called triggers, and that reduces the background up to some level. And we select a good quality of data. And then we out of these events that we have selected, which has passed these triggers are basically tuned to find a particular topology or particular analysis topology. So in this case, as we are searching for 4 photons, so we have created a particular trigger which can actually trigger only when these kinds of events occurs in the detector. And we have object selections. So in this case, in the final state, we have photons. So we apply some photon identification criterion on the objects, and we only select those which passes the identification criterion. And also as we understand that for the photons in CMS, we do not properly know the primary vertex from which this photons has originated. So we actually select multiple vertices, possible vertices among all the collision vertex that has been created in a particular collision bunch crossing. And we select the best vertex and the worst vertex depending on some multivariate analysis that we have performed using the different topology of the event, like number of tracks and etc., the PT valence of the jets. So using all these variables, we actually also assign some selections depending on the vertex that we choose, the quality of the vertex that we choose, and basically that improves the diphoton invariant mass resolution. And also we from those photons, we then pair the photons and reconstruct the pseudoscalar mass, and from the pseudoscalar mass we reconstruct the Higgs mass from the 4 photons. And then finally, from when these events are selected, then we try to categorize the events to improve the sensitivity, because we know that in some phase space of this analysis, the background level is high, and in some space the background may be low, and we try to either train some classifier or use some variable which already can distinguish between these two types of events, like signal and background. And in this case, the backgrounds are mainly coming from the QCD and diphoton plus jets or photon plus jets events. So we try to distinguish between these Higgs to pseudoscalar to 4 photon signal samples or events from the known standard model backgrounds using some multivariate technique. And we use that to separate these two event as much as possible, and which gives us better significance and sensitivity to perform this search. And finally, after doing this categorization, we perform unbin likelihood fit of the 4 photon invariant mass distribution, and yeah, so that gives us the exclusion limit for this analysis. So as I already explained, that a boosted decision tree is trained to perform this classification of 2 kinds of events, background and signal. So as you can see, the performance of this boosted decision tree for different mass points, like in this case on the left we have MA equal to 15 GeV, and on the right we have MA equal to 50 GeV, and actually it is trained for all these mass points separately. And we see that the separation between the signal and background is quite well. And in the rightmost bins, we have a good significance compared to the left ones. And depending on yes,
this is 20-minute mark. Just to tell you, you can take 5 to 7 more minutes. Yeah.
Okay. And then the signal distribution, which is the 4-photon invariant mass, is parameterized using some analytic function. In this case, we have used Gaussian with polynomial tails to fit this distribution. And as you can see, I mean, this is peaking at around 125 GeV, and the effective width of this distribution is around 2 GeV. And this we use as the signal model for the final statistical inference. And the background parameterization is done using some analytical functions. But in this case, as you can see, I mean, multiple functions can fit the background well. So we try to understand which function is fitting it best, and then from the list of best fitting functions, we actually also try to estimate some uncertainty due to the specific function that we have chosen, so that there is no bias that we introduce by choosing a specific function or family of functions. And as you see here, the data points, this is again the invariant mass distribution of the 4 photons, and the points are data, and we have a falling distribution, which is background, and we have a peak on the right hand side plot, which is the signal. And this is the final fit that we perform on the data with the signal and background model. We do the simultaneous fit, and then from that we calculate the rate of the signal, and we estimate the limit on the signal process. And as you can see, we here have calculated the limit from 15 to 60 GeV per every 1 GeV grid, and the limit is given on cross section times branching ratio, and there is no deviation from the null hypothesis, which is the standard model in this case, is found. And this is with the full 132G 2 femtobarn inverse data, which is the full run to data. But as I said, that this is only one topology, but we are still analyzing the boosted topology, which is also something very interesting, and the results will come out soon. Okay, so the next analysis, which I will talk about briefly, is the Higgs to diphoton. And in this case, again, the same process or same path is followed as I told in the previous case. So we have the trigger, which selects the events, and then we perform some categorization. And in this case, the categorization is done using, again, some multivariate analysis technique, which uses the event information from the diphoton system, and the recoiling jets, and etc. And as we see here, the distribution of the diphoton BDT score for the signal which are peaking near 1, and the background, which are in this case the jet or gamma jet or diphoton prompt photon background, they are peaking near, sorry, prompt photon is also peaking near +1, but other kinds of fake photon backgrounds are peaking near 0. And this is almost similar to the normal Higgs to gamma gamma search, which is performed between 110 to 180. In this case, the search is performed below 110 up to 70 or 65, depending on the data taking years, because we change the trigger conditions in some year in run 2, and that is why we improved the sensitivity in the very low mass invariant mass diphoton invariant mass region. So we could reduce the, or we could improve the window of invariant mass in which this was searched. And as you can see, I mean, this is the 2016 plus run one result, as we already have probably seen multiple times in some conferences, that it has shown some small excess, which is about local 2.8 sigma, around 95.3 GeV, and only you can see the run one was around 97.6 GeV, and run 2 2016 only gave a local significance of 2.9, around 95.3. After combining the two, we have got 2.8 sigma at 95.3. Now going forward to the next analysis, which is the Higgs to one. So this is 2 HDM plus S. So we have a HS, which is the singlet Higgs, and then these two decays into tau tau and BB bar, and yeah, I mean, so this is motivated from the NMSSM, and this is one kind of an event that where you can see that one tau is decayed into muon, and three jets. One is from tau, and the other two are from B jets. And in this case, again, the events are categorized first based on the final state topology. So the taus can decay either semi-electronically or fully hadronically. And then okay, so we in this case use, again, like for photon identification, we use some tau and B jet identification to select the jets, and then we perform a multi-class classifier for selecting, identifying signal and several background channels, and that actually acts as a discriminator in this case, and we use that observable, the output of the multi-class classifier, as a observable for the maximum likelihood fit for signal extraction.
Yeah.
And
how many minutes?
Yes,
more?
I probably have 2-3 more slides.
Okay.
Sorry. So the major backgrounds in this case are the real hadronic tau, or QCD jet, or WZ decaying to electron or muon. And in the first two cases, the background is estimated from the data-driven technique, and the last one, the background is estimated from Monte Carlo simulation. I'm not going through into the details of how it is done, but this is a new technique that has been used for this analysis, and this has actually improved the sensitivity of this analysis. And as you see, I mean, these are the output of the multi-class classifier that I was talking about, and this is the distribution. And as you again can see that the signal is peaking near +1, and the background is almost flat in this region, but there is a peak around 0.4, and there is some separation between these two. And if you look at the significance, as I said, that after using this kind of a classifier, the significance improves a lot in the last few bins, as you can see. And after so using that observable, we do the unbound likelihood fit, and from that we actually calculate the limit for different mass points. So these different mass points are for M capital H, and the x-axis is M small hs, and these are the limits. Actually, these limits are multiplied by 10 for each, so that it can be plotted in a same canvas. So, but what we can see is that almost in all cases, they agree with the standard model expectation, And by this search, we basically, okay, so before going to that, so the upper limit is set at 125 femtobarn for 240 GeV MH and 2.7 femtobarn for 3 TeV. And also it constrains the MH, MHS phase space. And as we can see that it actually excludes the existence of these kinds of a particle between for MH between 400 to 620 and for M small hs between 60 to 250. And also we have got some, sorry for the resolution, I don't know why, but we have got some exclusion on the MH, as you can see, which is the expected value is around 560, sorry 570, and okay, so which comes to the conclusion of my talk. So for many analyses, the full run-to datasets are not still analyzed yet. So we are waiting for more results and more direct search of additional Higgs bosons above and below 125 GeV expected from full LHC luminosity. And also we are going to take gather more data in run 3 and also in HL-LHC. And we are still involved in improving the analysis techniques, like identification of the heavy flavored jets, and also some photon identification technique using the low level information from the detector. And that with that we hope to improve the analysis and the reach of these analysis by more multiple fold compared to what we have now. And for that we need to stay tuned. And by that I just end my talk and thank you, and please ask questions if you have.
Thank you, Arnab. Do we have some questions here? Please raise your hand or just unmute your mic and ask. Right. Yeah, looks like there are no questions. So I have one little one. So you did all this, that is, you presented all the searches, but you did not, to best of my understanding, did not converted the results to indicate what heavy Higgs of the SUSY model would say and corresponding parameter spaces. So have you been involved in some of those analyses?
You mean the heavy Higgs ones?
Yeah, heavy Higgs, the H and A or something like that, which is from these circles.
Yeah, so no, I'm not involved, but what I found is that there is no new results on those. We have only 2016 data results, and most of them are being analyzed right now. Yeah. And as I said, I mean, we are soon going to have more results on the full run-to data.
Okay. Okay, so thank you. Thanks for your presentation.